Hello and welcome to this extra section on the NanoEdge AI Studio Datalogging MOOC. In this MOOC, all hands-on were based on the STWin KT1B evaluation board, since this has a large number of embedded sensor types that fits the purpose of datalogging. However, any other board can, of course, be used for datalogging. In this video, we will review the setup and configuration of a datalogging application, as well as a detection application, as we did in the MOOC in the first place, but using another STM32 MCU, which is the STM32L073RZ, and another sensor, which is a current sensor. So in practice, we will redo what we did in Chapter 5 and Chapter 8 of the original MOOC, but using a different hardware setup. The hardware setup is basically the following. We will use the NUCLEO L073RZ development kit and the NUCLEO IKA01A1 that will be plugged on this NUCLEO board. So this shield is able to get a power supply and to give it as output on the USB-A connector. So we will plug a fan on this connector and we will retrieve the current consumption through the ADC of the NUCLEO L073 board. So for all the details of what is capable of this NUCLEO IKA board, please go to this link, and the full description of the L073 NUCLEO board is on this link just below. So here is the actual hardware. So we have the L073 NUCLEO board that we will unbox. The shield that will allow to do the current consumption measurements. It can be plugged on the Morpho connector directly on the NUCLEO. So like this. Then we will need two USB cable, one a mini USB cable to power up the NUCLEO board, one micro USB plug to power up the shield, and finally a USB fan, but can be any other USB powered device that will be power supplied by this USB-A connector. So you can see here that I'm able to power up the fan. The agenda is the following. We will first review the STM32CubeMX project. This is fully described in this slide set. So we create it from scratch. We have all the guidelines to recreate this CubeMX project. In this session, we will only review the main part of it. Then we will open the STM32 associated CubeIDE project, in which we will have the dedicated code that is not handled by the CubeMX, which is the datalogging functions, the USART redirection functions to redirect the printf calls to the USART, exactly as we did in the MOOC in the first place, as well as the detection application, so the calls to the NanoEdge AI C library to detect either an anomaly or a classification. We will provide in this CubeIDE project two libraries generated by the NanoEdge AI Studio. But note that the generation of this library, so the data logging and the benchmark that has been done, will not be described in this session. It is already described in the MOOC, so the principle is exactly the same. I will specify, however, the settings and the number of signals that are used to create these libraries, but they are only provided here so that the project is functional in both cases, anomaly detection and classification. The idea here is to provide you with a functional project, but then the data logging is on your side because you may not want to detect the speed of a fan in practice. So you will have to define your own sensor and your own use case. And finally, we will build and run the data logging and detection application. You will see that the STM32 CubeIDE project has three different configurations that will enable specific part of the source code, that will enable either only the data logging or data logging plus anomaly detection or data logging plus classification. So in the materials section of the MOOC, you will find this archive. So it will maybe be embedded in a global archive of the materials or separated. So this is the base project we'll use in this video. So let's unzip it and open the CubeMX project. As already mentioned, this CubeMX project, the creation of this project is fully detailed step by step in the accompanying slide set. So you can see here that very few components, few peripherals are enabled. We have the ADC that will capture the current consumption on an input channel 4, and the USART that will be used to output, to redirect the printf calls to have a trace, a log of the captured data. So this is basically the main components that needs to be defined in this project. Then generate code have been called, and we will immediately switch to the CubeIDE project. So I will generate the code again. And at this step, I can already open the CubeIDE project. Of course, do not hesitate to pause the video because I will fast forward the compilation step, the opening steps. So if you are doing the lab, the hands-on at the same time, just pause the video to open on your side. So you have to select a workspace for CubeIDE. So we can see here our project. Maybe just some word on the project configuration. So we selected the CubeIDE IDE. All the peripherals are initialized in the main.c. Did not check this option here. This is a difference with the MOOC version, where we used this option to generate a specific file for each peripheral configuration, and the clocking is the default one. So let's review now the CubeIDE project. So what has been modified compared to what has been generated automatically by CubeMX is only the main.c file. So you will see that there is some specific compilation flag that are defined, and all the modifications are done within the user code begin and end section. That means that when we will regenerate the code from CubeMX, this section will not be touched. Only the sections that are outside this section are touched. So if you put anything within a user code begin and end comment, the code will be untouched by the CubeMX generation. What has been added also is these two folders. So this will be for the detection part of the application. It contains the library that has been generated by the NanoEdge AI Studio. So please refer to the MOOC for the details on that. For the anomaly detection, it's one library corresponding to the model that has been chosen after the benchmark, and an include file. And for the N-class classification use case, it's also one library and two include files, and one containing the knowledge, since the classification is a static knowledge. There is no learning phase. So let's review quickly before exploring the source code. What does this compilation flag correspond to in terms of state machine? First, you will notice that in this project, there are three build configurations. There is one for data logging, one for anomaly detection, and one for N-class detection. And each of these configurations implies a specific defines and specific include path, and also specific library path. To have a quick look, you can go in the properties of the project, in the C++ settings, and you can see here that I'm in data logging configuration. In this case, this enable data logging compilation flag is defined. If I switch to the anomaly detection, there will be enable data logging, but also enable detection. And it's the same for the library. In this case, for data logging, there is no external library needed. But if you go to anomaly detection, you will see that we are referring to the NanoEdge AI library in the AD, so for anomaly detection, library folder. And for the N-class class detection, it will be in the N-class folder. And it's the same for the include pass, where this specific folder containing the dedicated include file is specified. So as mentioned, there are three build configurations, one for data logging, one for anomaly detection, and one for N-class detection. So each of these configurations will correspond to specific source code and will correspond also to a specific state machine of the application. We try to keep it as simple as possible. You are free to extend it to make it more complex and more suitable to your case, of course. So for the data logging, when the board is reset, forward on, the data logging starts immediately. And when you press the user button, it goes to idle mode. And when you press again the user button, it goes back to data logging. That's the only thing that this configuration does, just do with the data logging. For the anomaly detection, so we have two specific compilation flag, a specific include pass and a specific library pass. And the state machine is after board reset, again, we go to data logging. When the user button is pressed, the learning phase is launched for default 50 iteration. And after this learning phase, so it's still logging some information on the USART. And after this learning phase, the detection phase is started. And the press of a button goes back to the learning phase. The only way to go back to the logging, to the data logging, is to power off the board and power on again. And finally, for the N-class classification, so three compilation flags are needed, a specific include pass and a specific library pass. And there is no learning for the classification use case. So after board reset, we go in a logging state. So the data from the ADC is logged to the USART, and the press of the button just switch to the detecting phase, so detecting which class is currently running. So let's now quickly review the actual source code so that you can see that it is quite simple. There is nothing very complex to get a first data logging application or a detection application. So we are in the data logging configuration. We include the stdio.h file. This is for the printf definition. We define the number of axes, so it's only one axis because we have only one value, which is the current consumption. And the buffer size is 512, can be less, could be less, in fact, could be more also. It depends on the use case. This has to be tested on your specific use case. And we have a set of defines which are linked to the sensor output data rate, to the size of the signals, of course, which is the number of signals multiplied by the number of axes. And some other information for this is the LED is just for an informative signal to show that what is going on. If it's you can see directly looking at the board, if you can see the LED below the shield to see if it's in logging mode or not. There is a simple state machine. The state machine for the data logging is only log and idle. You can see that there is also a learn state when we are in enable detection, so for anomaly detection, and an inference state to where we are in detection. And this learn state is disabled when we are in N-class detection because it's static learning. Then this is the default state, so it's logging for the three possible configurations. This part is specific to the N-class detection. We will enable it just after, but this is already described in the MOOC in the last chapter 8. These lines need to be copied from the generated include file of the N-class classification use case before compiling. So it's not automatic. That's why there is a specific pragma here that warns the user that this must be copied. So it's only a warning. So it will be displayed on at compilation step, just to help you not to forget to copy these lines. This is automatically generated by the CubeMX project. What we added is the fill buffer and print buffer and the log buffer. Fill buffer function, print buffer function, and log buffer function. This is the function that will redirect the printf to the USART. So the _write function is called automatically by the printf, can be redefined. So that's exactly what we do here. And we redefine it to transmit to USART. What is specific to data logging and detection is the calibration of the IDC and the start of the IDC based on the timer 6. And then that's all for the data logging. And what will be called in a while loop is this switch case statement depending on the state machine. So by default it will be log, and if we go to log using the control key, the log will change the led period to indicate that logging is ongoing. We'll fill the buffer, the current buffer. It's a local variable, an array. So calling the ADC get value using the size of the buffer that we defined at the very beginning of this main.c file, and the print buffer that will only call a printf on the capture the data. Of course, adding a \n, which is a way to indicate a new line. This is required by the NanoEdge AI Studio as described in the global MOOC. So let's build and run this program. So the program is built, and we can now launch a debug session. So you can see that 3 debug sessions are configured because they correspond to 3 different binary files. So I will use this one. So now the program should already run. So I can launch a teraterm session. So it's just a serial comport listener. So the COM22 appear as soon as the board was connected. And we can see already some characters. So this is the printf that we call from the data logging application. They are nonsense because the speed by default is not the right one. I have to set it to 115,000 baud rate. And now we can see the data logging. So that's the first configuration. I will pause it. To switch to another configuration for detection, for example, so remember that there is already a library. So this needs to be generated by the NanoEdge AI Studio as described in the MOOC. So I use the data logging function to capture the normal state, which is the fan running at speed 1, and also captured some different speed, and including the off state of the fan for the non-regular signals, and then generated the associated library with the best model to get the best accuracy. So to change the configuration, you go to set active and select the anomaly detection, rebuild, and program the board. So we'll launch a debug session this time. I select data logging, no, anomaly detection, sorry, and launch the debug session. So for the moment, it's still logging. It will stop when the board will be programmed. So here it stopped. So the board is being programmed in the background, and a breakpoint will be put at the beginning of the main function. So let's put this window aside and start the application. So the application starts data logging, as we saw in the state machine. And when I will press the user button, it will start to learn. So I will put my fan in speed 1 and start the learning. So here you can see that there is only 30 steps of learning. I changed it to be faster, in fact, but you will see what is the drawback of having too low number of learning. So it will be faster, of course. So now the similarity is 100%. So what's happening if I change the speed to speed 2? Okay, anomaly is detected, perfect. Speed 3 as well. And if I turn off the fan, it's also an anomaly. And but if I go back to speed 1, you can see that, okay, first the similarity is good and it goes down. It's not so good, in fact, and it's even detected as an anomaly. So what I will do then is to launch another learning step. Because remember that the library that is generated by the NanoEdge Studio in case of anomaly detection is only the model that will be used to learn, to detect an anomaly. There is no knowledge of an anomaly. So it's able to work on this on the signals that we will provide, but it does not know yet which signal corresponds to an anomaly, which does not. So if now I switch to another speed, it's still an anomaly, of course. And normally, speed 1, we should get better result because we learned more. Each time you press the user button, you add some learning to the current learning. So finally, let's see the last configuration, which is the N-class classification. So I will change the configuration to N-class detection and build a project and program the board. So here the classification has been done on 20 signals for each speed. It's not a lot, but we can see that already we have some good results because, of course, in terms of current consumption, the variation of the current consumption depending on the speed are very obvious. To be honest, we do not really need artificial intelligence to distinguish fan speeds using current consumption. This is only an example that is provided. The purpose of this is to show how easy it is to implement an application on top of an existing one that can use AI to detect, to use input signals and do some anomaly detection or classification. So let's launch a debug session. This is another way to launch it. So you see that there are 3 possible binary files. I will take the N-class classification. So the logging will stop when the board will be programmed. And I will even turn off the fan. So remember the state machine, the first state will be a data logging. So again, we will see each signal that are currently captured by the ADC, and pressing the user button will switch to classification. So the fan off is detected. If I press and put in speed 1, you can see there was a glitch. At some point, the class was not properly detected when I press the button because there may be a higher consumption when just turning on the fan. If I press speed 2 is detected, and hopefully speed 3 is detected. So with this project, you have a basic project that you can reuse on this very hardware setup, but also on your own setup. All you have to do is to configure, of course, your MCU and the specific peripheral that is used to capture the sensor you selected. Maybe it will not be ADC, maybe it will be through I2C or SPI. That will depend on which sensor you are using. But the main purpose of this video is to provide and show you how to implement a data logging function. So the code is pretty simple. there is a main field buffer function that will call your sensor function to retrieve the value. And all this will be initialized based on the signal data size. And then you will have also your own sensor output data rate and maybe specific axis number. So that's it for this video. I hope it was useful for you. So you now have the full project to do your own manipulation. One last point that I mentioned for the N-class classification, you can see that if I rebuild this project, I will get a warning. And this is on purpose. Warning, the following line must be copy-pasted from the NanoEdge AI.h. And if we go, so these lines are concerned. These lines, and just to show you where they are, so they are in the N-class. Here it's the folder, I named it N-class for the classification, and in the NanoEdge AI.h you have a comment here. So this is the lines that must be copied into the main.c, and it's not automatic. So this is the end of this extra section of the NanoEdge AI Studio datalogging MOOC. Some other may come in the future. So let's see. And in the meantime, I wish you a pleasant day, and I hope you enjoyed this video.